Agency of Indonesia, and today I am serving as a moderator for today colloquiums. So for your information, we basically organize our quantum physics colloquium 2 times every month, and we invite speaker not only from our research center, but also guest speaker from other institutions. So for today, we are pleased to have Dr. Saeed Jahromi as our guest speaker from Multiverse Computing in Spain. So Dr. Saeed Jahromi will speak about the quantum computing for finance. And this talk will discuss about how quantum algorithm like quantum optimization, quantum machine learning, and also quantum amplitude estimations over the advantage over traditional methods. So the presentation also will highlight the recent advances in quantum-inspired technique such as Tensor Network and also their successful application to the finance data. So it's my pleasure to welcoming Dr. Saeed Jahromi. And hello, Saeed. So are you ready
Hello,
for your
everyone.
presentation? So thank you so much again for being with us today. And first, you have already share screen, right? So before we start presentation, please allow me to briefly introduce our speaker today. So Dr. Saeed Jahromi obtained his Ph.D. in condensed matter physics in 2014 through a collaboration between he and Tosi University of Technology in Iran and the University and Technical University TU of Dortmund in Germany. So he has experience in academia and also industry with expertise in quantum computing, quantum many-body systems, tensor network algorithm, and quantum machine learning. And he has several postdoctoral experience. His first postdoc was at Sharif University of Technology, Iran, from 2015 to 2018. Then he continued his postdoc at EPFL, Switzerland, from 2018 to 2019. And after that, he continued his postdoc at Donostia International Physics Center, Spain, from 2019 to 2021. So after experiencing several postdoc positions, he decided to join Multiverse Computing as a principal scientist from 2021 to 2024. And then starting from 2024, he has been promoted as Associate Research Director at Multiverse Computing. So with that, Dr. Saeed, are you ready for your presentation today?
Sure. So
So,
I'll be
okay.
glad to be with you.
So, okay, you have 1 hour for your presentation and 30 minutes for the question and answer sessions. So please be informed to all the participants. If you have any question during the presentation, please post your question in the Zoom chat. Dr. Saeed, if there are any questions that appear in the Zoom chat during your presentation, please ignore them as I will read the question after your finished presentations. So if so, Dr. Saeed, the floor is yours.
Thank you very much. And hello, everyone. I'm glad to be here with you. And I think I should say good afternoon for Indonesia. Today I'm going to first basically briefly give you an introduction of the Multiverse Computing, the company, and then basically deep dive into the quantum applications. Also, basically, I will tell you how we build this company from ground based on the science of quantum technology that and having the following the ideas that we had to basically make quantum solution available for everybody. That's why actually Multiverse originally was established. I will focus mostly on different application of quantum computing, especially quantum optimization, which are, I would say, the most promising approach for the moment that can have application for finance sectors nowadays. And then give you an example of portfolio optimization, which is basically can be a very interesting and useful problems for many financial institutions. I will also introduce the quantum-inspired tensor network methods, which are ideas from quantum physics, but it runs on classical computer, and it can bring a real value for today's market, especially for many different problems, especially financial problem. And in the end, I will tell you what we have developed in our company to basically make solutions of quantum and quantum-inspired computing for different sectors such as financial sectors and optimization and basically artificial intelligence, and give you some ideas that how we can actually bridge between the world of quantum to the AI to also bring extra solution for the future of industry and academia. Okay, so first of all, the company. So Multiverse was established 6 years ago. Actually, we celebrated Multiverse birthday 2 days ago. The sixth birthday of Multiverse. Multiverse was started as a spin-off of a research center at Spain, Donostia International Physics Center. And our strategy and our aim was to develop a high-performance quantum and quantum-inspired and AI solution that could solve real-world problems now. So we build basically software which are useful for not only today's computer, but also for the future quantum computers that become ideal and available everywhere. So the company is composed of 150 people, more than 40 nationality, more than 20% of the people that have PhDs, and we have a very strong publication record and citation record, and the company has a great revenue that basically supports the ongoing efforts of the company for the future years. And we have more than 50 clients that actually are using our solutions, quantum and quantum-inspired solution, for their daily challenges. So the headquarters of the company is based on Spain, in the north of Spain, actually in the San Sebastian, which is this it's a beautiful city of San Sebastian. It's a very ideal place in Spain to both work and do research. So we have also a global presence. We have headquarters in Spain, but the offices of tech are in Canada, France, and Germany. We also have sales offices in UK, Italy, and US, which give us a very good global presence to collaborate with people. So I encourage you and also invite you guys, if you have ever came to Spain, you're fully welcome to both come for a holiday or also visit us at the Donostia. It's a very beautiful city here. And what we do at Multiverse, we actually offer solutions, both quantum and quantum-inspired solution for solving many interesting problems regarding the basically machine learning, AI, and basically quantum algorithm that can have application in many different sectors. So we offer two different kind of solutions. We offer quantum algorithm and quantum solutions and quantum softwares that runs on the real hardware, such as, for example, the D-Wave computers. But of course, as we currently know, we are in the NISQ area, or noisy intermediate small scale quantum computer, which may not be ideal and suitable, but still we have the software and the solution. Especially this is important for many of the companies that want to explore the opportunities of quantum for their problems that they want to solve. But also we offer quantum-inspired or tensor network solution that actually, these are the techniques that are coming from ideas from quantum physics, but they are running on classical computers, supercomputing centers, and you can actually benefit from them today. And they basically provide very high quality and remarkably fast results for the solutions that is available now today that can bring actually commercial value for the client and customers. So we also have problems in different areas. So like we tackle problems in optimization, such as logistics, finance, telecommunication. We also do simulation. So basically these are the application of hopefully future quantum computers that we also try to build solution for these kind of problems nowadays. So like for simulation, we target fluid dynamics, material simulation, which have application in material and drug discovery. We also have a very big team of financial engineers that work in different sectors in finance, such as in fraud detection, portfolio optimization, and also predicting optimization problems in the energy market. And also we are active in security and cybersecurity to use a quantum solution for better and more secure world. Okay, so now after this introduction, I will give you some basic ideas on what we actually can do with quantum computing, or later with quantum-inspired computing, and how we can use it specifically for finance problems. Okay, so I think it is needless to say, if you today open the web page of any website and Google the application of quantum computing, you can really find many fascinating applications in different areas, such as in material science simulation, quantum chemistry, optimization, machine learning, and in finance, that each one of them basically can have many subcategories of different problems that are interesting and important for the different sectors, but yet they are very challenging and difficult problems that many of them are beyond the capabilities of classical computers that are available nowadays. Especially one important one is the finance sector, which is the interest of today's talk. And this is a sector that actually has a lot of interesting and important problems, and many entities are interested for working and exploring quantum solution for the finance sector. For example, banks, central banks of different countries, financial departments, rating agencies, regulators, tax offices. These are all of the agents, or maybe some of the agencies that one way or another deals with different kind of problems in the finance sector, from risk analysis, fraud detection, basically portfolio optimization, and these kind of problems that actually all deals with financial transaction. And there are many interesting problems here that we can target and solve. And quantum computing is one of the most interesting and promising approaches that actually can bring value even today, even with the current basically non-optimal quantum computers that we already have in the market. And why is the case? Is because why is quantum computing interesting for finance? And the reason is that finance is full of hard problems that are challenging for classical computers. So I will show some of them basically here, and but most importantly, the market actually deals with many different parameters that make the problems that you might have in the finance sector very complicated. Basically, finance deals with uncertainty and basically a future behavior of an asset, and the prices and return that you may have in future. Okay, so a financial institution may deal with a lot of assets that they may be correlated. They create together a very complex system, and basically their overall behavior is very complicated. It is very difficult to predict basically the different assets, how they perform during time, how they perform with respect to each other. And also you should consider, when you're dealing with financial problems, basically you have to consider some certain volatility in the market, some risk threshold, some profit margin that you would like to have. And these kind of things make a very multidimensional, complicated problem space that providing different solutions for different problems are very difficult. However, the good thing about the financial market and these kind of problems is that they are strongly mathematical. It means that there are basically strong mathematical theories behind many of the models that can predict and analyze the behavior of the market. So this means that you can actually have optimization problems or basically problems that are stochastic, and then you can use Monte Carlo or sampling for solving those solutions, or you have a stochastic differential equations that can be solved with approaches for solving partial differential equation, and also you can design machine learning approaches based on the mathematical models that you can find for predicting the market. Actually, for the good reason of having a strong mathematical basis, there is a field in economic which is called quantitative finance that actually tells you, which is the science of studying the mathematical model for predicting the market. So here we will also benefit from some of them to see how we can actually solve real world problems with quantum computers. Okay, so in principle, many of the problems that you can find in financial industry and in the finance sector can be more or less categorized in these three different sectors. So, for example, you could you could ask some kind of questions, and then depending on the type of the question, you could basically categorize it, categorize this question or this problem into a different sector. What kind of problem is this? For example, you could say that which asset in my portfolio should be included in an optimum portfolio, and how should one change its composition according to the market? For example, you have multiple assets, you want to decide which one to sell, which one to buy, and what is the best optimum composition of this portfolio. This is a type of optimization problem that it is very widely used, and many financial models can be modeled with this kind of optimization problem. Another kind of question that you can ask is how to detect opportunities in the different assets in the market and take profit by trading them. So this is something that basically requires the learning from the behaviors of the market and the behavior of the assets. So when you deal with this kind of learning from the behavior of the market, probably machine learning techniques are one of the best that can actually comes into play and to help you to use different machine learning models to learn the market behavior and actually use it for predicting the market. The other kind of questions that you can ask is for example, how to estimate the risk of a portfolio, a company, or even the whole financial system. So to assess the risk, usually you have to basically investigate the market behavior, for example, over a period of time, and the market is basically behaving stochastically. So one of the approaches that you can use is basically you can simulate the market behavior with some Monte Carlo approach, and then according to that, analyze the risk of the financial problem that you have, or the risk of the portfolio, or the company that you are dealing with. So these are the kind of the category of the problems, or let's say typical problems that you can find in financial industry. And then so we know we have classical optimizer, different deep learning or machine learning model, and basically Monte Carlo technique. However, these three categories, while they may look simple, they are very challenging from the point of view of computational complexity, and many classical computers basically have a great challenge and difficulty to tackle these kind of problems. And the reason is that the problem space, the size of this problem, depending on the number of assets and the size of the market that you're going to study, can be very huge and gigantic. That's why classical computers may have a very difficult board, or at some difficult time solving these problems for you, or at some point it may be even impossible for classical computer to scale well and give you the best solution. That's why quantum computing can actually come into play. And then for any of these category of problem, you could have a quantum counterpart that bring a speed up and enhancement for you. For example, you could have, instead of the standard optimization, you could solve the optimization problem with a quantum computer. This falls into the category of quantum optimization problems. For machine learning, we have basically equivalent quantum machine learning techniques. And for Monte Carlo, we have quantum amplitude estimation, which basically helps to predict the probabilities of different distribution of market behavior. So among these three, one of them that I will focus most today is the quantum optimization problem. And the reason that I focus on this is because this is the most promising approach nowadays, given the hardware technology of available quantum computers that you can use to solve the problem with it. That's why the next focus in this talk is going to be on the quantum optimization. I will just comment on these other approaches, but I will give you some ideas how what are the typical approaches that you can basically use for quantum optimization, and particularly use it for solving the problems in the financial sector. Okay, so like here, I will focus mainly on 4 different approaches: quantum annealing, quantum approximate optimization algorithm, and variational quantum Eigen solvers. So these are all of the approaches that actually can be applied to, apply to the same quantum, or to the same quantum optimization problem. In the end, in a different section of the talk, I will also focus on quantum-inspired tensor network method for solving optimization problem. But I will come back to this in a separate section of the talk towards the end. But let's go and see what is quantum annealing and how it can work for basically solving an optimization problem. Okay, so what is quantum annealing? Actually, quantum annealing is a non-ideal implementation of adiabatic quantum computing. So, what is adiabatic quantum computing? The basics of adiabatic quantum computing is that if you have a basically 2 Hamiltonian, which is a fundamental structure of your problem. Later, I will say, for those who may not be coming from physics, Hamiltonians could be a cost function to your optimization problem. So H0 could be a Hamiltonian, which is ground state is unknown and easy. And then you have your problem Hamiltonian, which is another basically Hamiltonian, which can be complicated, and the ground state might be challenging or unknown. And you can have a tuning parameter S that, for example, varies over time. You could, if you start from the ground state of this H0, which is a simple and easy Hamiltonian. So, for example, an example could be here. So if you are familiar with the magnetic system and the Ising model, so this is called the Ising model. This could be some binary variable, or in the terms of the qubit, it could be some bits that could be zeros or 1. And then the solution to the ground state of this could be some spins that point all in the same direction. And then if you are in the ground state of this H0, and very slowly you change the parameter S in your system, such that this S is very slow, and the variation in your basically the variation that S imposes is not larger than the energy bound gap of the system, it is guaranteed, according to the adiabatic theorem, that you always remain in the ground state. And then if you tune this S very slowly, you end up from the ground state of E0 to the ground state to the ground state of H0 to the ground state of HP, which is your problem. Okay, so this is what adiabatic quantum computing does. However, in our noisy and non-ideal quantum computers currently today, such as, for example, the D-Wave. So D-Wave is a big quantum hardware provider that works on basically providing quantum annealing solution, and they have noisy qubit, but they are suitable for these kind of problems. So in the quantum annealing, this process is not so slow, such as the adiabatic quantum computing. That's why it can be fast, because you want to reach the solution faster. However, the drawback is that since you do this evolution of S and changing of S going from H0 to HP, the problem is that you may not always end up to the actual and exact or global minimum or global solution of HP. That's why what you can do is that you can repeat this process many times and sample from the final solution. For example, this could be your energy landscape. If you do it very fast, you may end up into any of these basically local minimas, and then you can basically analyze each one of them and choose the one with lowest energy as the solution to your problem. Regarding the solution, and also the problem, usually optimization problems requires a cost function. What we do in quantum computing is that one of the easiest Hamiltonian or problems that we can solve with quantum computing is this problem of Ising model. So here, this term is basically called the Ising term, which is basically 2 variables that can basically be correlated with some correlation matrix, and then we might have some basically terms or some constraint and or some penalty terms that basically changes the correlation between these two guys and then controls the optimization problem. So basically what we would do in mapping the optimization problem to from classical computer to optimization problems on a quantum computer is typically we are interested to map our optimization cost function to an Ising Hamiltonian, which is similar to this one. Okay, so this is actually later I will show you that this is a kind of problem that in optimization it is called Kubo problem or quadratic unconstrained binary optimization problem. So this is a type of problem that quantum annealers can do. For example, if you want to know about the hardware side, the D-Wave is one of the companies that actually provides hardwares for quantum annealing. Also, I think the other generation of quantum computers that can do this kind of operation or quantum annealings are the atomic quantum simulators or ion traps or neutral atom quantum computer. This generation of quantum computers are capable of solving this quantum annealing and optimization problem. Actually, for example, D-Wave's machines are designed mainly to minimize the cost function in terms of a Hamiltonian, which you can see here. Okay, so now we would go to the next approach, which is quantum approximate optimization algorithm, or QAOA. Sometimes it is also pronounced QAOA, which is basically a discrete version of basically quantum annealing or adiabatic evolution by following discrete optimized step. Again, in this problem, we would also have some H0, which is some Hamiltonian that its ground state or is easy or known, and HP is our final Hamiltonian or the cost function of our problem. What we would do for this kind of optimization, we map the optimization problem to a Hamiltonian, which is the cost function of our problem. But instead of going like in a smooth or continuous way from different trajectories to end up to the final solution, we actually discretize it, and then we end up to the final solution. It is a hybrid algorithm that some part of it run on a quantum computer, some part of it run on a classical computer. The idea actually, the idea is that you basically break the Hamiltonian or cost function of your problem into basically different steps, or do you do torotorize them or do torotor decomposition and create some unitaries and apply, so start from some initial state, which could be the ground state of this H0, and then alternatively apply some quantum circuit, which is basically these terms in your cost function. So alternatively, you just apply e to the power minus I HP with some basically a parameter beta, which you should fine tune. So basically, this is a parameterized circuit that you have to fine tune on a classical computer. And then alternatively, you apply the Hamiltonian of your problem and then the Hamiltonian of the initial part. And then you do this because basically this part, sometimes it is called mixing Hamiltonian. It is because we want to guarantee that we don't get stuck in a local minima. That's why this Hamiltonian applies on the states once in a while and in an alternative way, and mixes the solution space so that you don't get stuck in a basically local minima. The good thing, and basically these circuits are the parameterized circuits. So basically you apply them on a quantum computer, but then you find some solution here, you do the measurement, you feed this measurement to a classical optimizer, fine tune these alpha and beta parameters such that the cost function basically is lower. And then you repeat this in an iterative way until you find the optimal solution. There are some good things and bad things about this approach. The good thing is that basically, since you are applying directly the Hamiltonian of your problem to the circuit, then the correct entanglement or quantum entanglement structure will be captured in this variational quantum circuit. However, the bad thing is that basically this circuit might be very difficult to implement, because if the architecture of your Hamiltonian is very difficult, then you have to later transform these unitary gates in terms of Pauli operator, and this is not always an easy task. That's why the other variational algorithm has been also created, which is called variational quantum eigensolver. In this approach, we try to replace the previous circuits, which were very difficult, with the desired parameterized circuit that we could easily fine-tune and optimize on a classical computer. However, here again, similar to the previous case, we also need a cost function, which is the Hamiltonian of our problem. And then we apply this Hamiltonian to some states and then calculate the expectation value of the Hamiltonian. So basically, energy of the Hamiltonian is our cost function that we want to minimize. We do this minimization on a quantum computer. We calculate this, we calculate this expectation value of the energy on a quantum computer. However, then we feed the results to a classical optimizer that basically finds these theta parameters, which are the parameters of this parameterized circuit, and we do iteratively do this optimization such that we find a solution. Again, this approach also has its good and bad advantages. So the good thing is that the circuit is now easy. Therefore, we can always implement it in a very efficient way. However, the bad thing is that this circuit that we implement may not be the optimal circuit or the best circuit, and may not be able to capture the correct entanglement between the parameter space. So then each one of these approaches have its own drawback and advantages. However, among these ones, for the case of optimization problems, as I will show you in future part of the talk, the D-wave one, which is based on quantum annealer, is more scalable and basically more easy to solve a larger scale problem in today's noisy hardware. Okay, so now let's go and see an example that how actually we used to solve a dynamical portfolio optimization problem. Okay, so what is the problem? The problem here is that we have a couple of assets over a period of time. So the problem is that we want to select the best distribution of assets that optimizes some objective function, that this objective function actually maximizes the expected return. So it means that we want to have the highest profit and minimizes the financial risk, such that the risk of having this profit is as low as possible. And then this is done for the distribution of assets over a period of time. That's why, since basically you are studying this optimization problem over a period of time, this could be some days or some years. So this is a dynamic optimization over time. That's why it is called the dynamic portfolio optimization. So for this, we can actually map our problem into a Hamiltonian. Hamiltonian is something that basically you can find in quantum physics easily, such as the one which is shown in the previous slide, the Ising problem. Okay, so we are trying to create a cost function for this Hamiltonian that is very similar to the Hamiltonian of an Ising model. So here, for example, these omega of t, these are the distribution of the assets over time. The mu is the profit. Gamma here is the basically volatility or the risk of the market. So this is the covariance basically matrix between these assets, the distribution of assets. We want to also have some, so the cost of the transaction in such a market has some cost. So lambda describes the cost. We also want to solve this optimization problem, which is with some constraints, such as, for example, the constraint here is that the total investment is fixed over the period of time. So which can be actually tuned by some Lagrange multiplier and some basically vector of constraint that we put here. Okay, so we want to solve it with a quantum computer, or basically with an optimizer that deals with qubits. So you know, qubits are discrete. They can have values like zeros and one. That's why you can. So, and the weights of these assets may be a continuous parameter. It can basically any number. That's why we can discretize them and represent them in terms of discrete variable in terms of discrete. So this is how we discretize some basically continuous parameters. So of course, if you want to map any continuous parameter in a quantum computer, you have to one way or another discretize it, and there are different type of discretization. So here is the one that was used for these assets. And then if you look at the type of this problem, so this Hamiltonian or this cost function is called a Kubo, a Hamiltonian or a Kubo cost function. So the reason which is called Kubo or quadratic unconstrained binary optimization problem is because basically there are these X transpose and X and some covariance matrix. So there are two of them here. So they are binary, and then they can basically be zeros or one. And these there are some covariant matrix that basically tells you what are the relation between these two. So, and if you compare it with the Ising magnet or the Ising Hamiltonian that I showed you previously, this is pretty much very similar to the Ising problem. That's why you see Si and Sj. So these are also the binary variables or spins or qubits on a quantum computer or in a physical system that used to simulate a magnet. And then this Ij, which is the correlation between these two, could be basically the same as the covariant matrix that you might have here. So consider it as a classical variable. These Si and Sj could be 0 or 1 or +1 or -1, and basically they can change between these two values. While it looks simple, this is a highly complicated problem to solve depending on the number of basically assets or the number of parameters or variables that you might have in your system. Actually, solving this kind of optimization problem is an NP-hard optimization problem that maybe for finite sizes you can basically solve on a classical computer with the standard available optimizer. But if you go to larger scale problems, it is going to go beyond the reach of any classical computer. So here I would like to get your attention to basically this paper. This was, I think, the very first paper that we did at Multiverse. Actually, Multiverse was born on top of this paper because we showed that quantum computing can have real application for financial industry and real problem. So this was a project that we did with the BBVA bank in Spain. And we solved this problem of the dynamic portfolio optimization using different techniques. We used different optimizers like classical optimizers, D-Wave optimizers, VQE, as well as the quantum inspired or tensor network optimizers that we created. And these are basically some numbers for the solution of for the problem space. So you can see basically these are the total number of variables that we could use. Basically, this is for over 8 years and 53 assets in our portfolio. And the cost function that I showed you in previous slide, the size of the solution space is 10 to the power 382. Such a huge problem space is not possible to be handled with any classical computer. However, there are techniques that basically based on D-Wave quantum annealers as well as our tensor network solution, which even make it not only possible on quantum computers, but also possible on classical computers based on tensor network methods. Okay, so these are some numbers as you can see. So basically X small, small, medium, large, X large, and double X large are basically the size of the asset. So getting back to here, you would see that, for example, we have two assets in our portfolio. For the X small, S for S is 5, and then for double X large is 53. And also the time period is also like 8 years, for example, here. Okay, and then you would see that a VQE, which is a quantum algorithm, this is, I think, for this problem, we use IBM gate-based quantum computers, which are limited and noisy. So we were able to solve very small size problem on this. Exhaustive is basically the classical problem that in an exhaustive way explore all of the possible solution and tries to find the optimal one. This will always give you the correct solution. However, it is very slow and very limited to a small scale problem. So another type of VQE with some constraint that we used also basically helped us to improve the solution size a little bit larger, but still not too much. GECO is or GECO is also another classical solver, which is a commercial solver for the optimizer that you can find in the market. And then we have the D-Wave hybrid and our tensor network method, which were the most successful ones and allows to go to basically very larger basically a number of assets over the period of time. And so basically these are the ratio of the I think profit with divided by the market risk. These are the profit itself that basically tells you for this portfolio optimization how much profit over for these 53 assets you could get. And then this is the runtime. And as you can see, so while the other approaches couldn't even reach the largest portfolio size, the D-Wave hybrid and tensor network were able to do that. The D-Wave hybrid, which is a quantum solution, this is in seconds, 171 seconds. However, our tensor network solution, so it took much longer. Let me also emphasize that this was the very first implementation of tensor network optimizer we developed like 6 years ago. Our tensor network optimizer nowadays is much more faster. It is running on supercomputing centers with GPUs, and this number nowadays has reduced to much smaller. So, and then basically the conclusion here was that not only quantum computers based on D-Wave solvers and the quantum annealing are very fast and good, but also they are very scalable and they are capable of basically solving larger scale problems. So we did also another collaboration with another bank, Bankia, which is another bank in Spain. And then we also solved a different type of basically quantum investment optimization problem. So here, this one was with the minimal holding period. So you hold your assets for a period of time, and after that you start selling them. And basically, it's a slightly different cost function, which you can also find here. We also solved it on the D-Waves and also with our tensor network solution. These are the results. So this is basically the market volatility, like 15%, 10%, 20%, or market risk. And then this is the profit that you can get. The best product, the best profits or product offered by well-known banks are in this here, around 20%. Like for example, for between 15 to 20% of market volatility, you would get like 20% profit, while our quantum solution actually tells you that you can even get higher profits. So it was a result from the data from 2019, and we showed that actually if you use quantum computer, you can have a better solution to your problem, and it will even give you more profit. It means that if you use a quantum computer and do a proper solution to this optimization problem, you can actually gain more money. So, which is a very valuable thing. And this is one of the biggest justification that basically tells us we should follow quantum solution for financial problems. So in a very a smaller amount of time, or a very shorter time, you can get a better solution for your portfolio optimization problem. So this was also featured in the D-Wave website, and also they advertised. So actually they said that going from the toy model, this was the very first application of the real world problem that basically was solved with the quantum computer. Okay, so and interestingly, so we were talking with our clients and with our friends in different banks. Well, of course, while they would like to know the details behind the scene, but many of them are not quantum physicists. They don't know details of the optimization problems. They only work with the Excel sheets and they deal with these numbers. So we created a Excel plugin for them that without leaving their familiar workspace, they can actually select the assets that they want to do. And then with this plugin, they allow them to set some parameters and then just click a button, and then this optimization problem will automatically be run on a quantum computer on a D-Wave, and then it gives them back the solution without leaving the Excel environment. And this is one of the things that we actually learn and try to tailor our solution for the real application and real people that are working in the market, in the banks or in a financial institution, because they wanted not only to use quantum, they wanted also to be easy. The one guy who is sitting in the bank, is employment of the bank, doesn't care about what is quantum. He just want to use some solution to get he just want to use some tools to get the solution faster and more accurate and bring more profit. That's why we had to offer them a solution which is very easy and simple to work with. Okay, so this was the things that we provided the solution, this kind of optimization on the quantum computers. However, we know that quantum computers still nowadays are noisy, they are not robust, they are not widely accessible, they are still very expensive, and it is not available to everybody. That's why it is good to have a solution that works on a classical computer, which is available nowadays. So that's why we created the Tensor Network optimizer for these kind of problems. So I will give you a brief introduction in the second part of the talk. What are Tensor Network and how you can solve an optimization problem? So first of all, it is called Tensor Network, but what is tensors? So I think if you are familiar with linear algebra and mathematics, you have always heard about tensors. Or if you are familiar with any programming language, you have seen that, for example, for Python, you have seen that NumPy ND arrays, okay? So n-dimensional arrays. Tensors are nothing but n-dimensional array of data or complex numbers. So a rank 0 tensor is basically a single number. A rank 1 tensor is a vector. A rank 2 tensor is a matrix. A rank 3 tensor and up to rank n are basically n-dimensional or multidimensional arrays that you can also have this graphical representation to show them. But going beyond 3, then you run out of these boxes to basically show them graphically. But for example, for an n-index or n-dimensional tensor, however, we have developed this when I say we, I mean the scientific tensor network community. Basically, it was they developed this graphical notation for representing n-dimensional tensors. That basically every tensor is an object, and the link is connected to that tensor according to the number of dimension of that tensor. For example, a scalar, which is a single number, it doesn't have any link connected to it because its dimension is 0. Vector has only 1 dimension, so there is 1 link connected to it. Matrix has 2 dimensions, so 2 link connected to it. And then tensor of rank 3 has 3 dimensions, and tensor of rank n has n dimension and n link connected to it. So not only this, the graphical representation helps to represent these tensors, but also they can be used for some mathematical operation between tensors, such as the matrix-matrix multiplication or matrix-vector multiplication, which is nothing but the sum over shared indices of these tensors. For example, a matrix-matrix multiplication is basically, for example, matrix R multiplied by matrix S, basically is nothing but the summation over the rows of R and columns of columns of R and rows of S, which is basically a simple summation, and then in the end you will have a matrix as the outcome. This can graphically be represented by connecting the line between these two tensors together. So whenever there is an interconnecting line, it means that there is a summation over these two tensors, these shared indices of these tensors, and then when you do the summation, this dimension goes away, and you end up with dimension alpha and gamma, which is basically the resulting matrix. So this operation is called tensor contraction, which is the extension of tensor or matrix-matrix multiplication or matrix-vector multiplication. And for the n-dimensional tensor, this operation is called generically contraction. So not only tensor networks help you to actually represent the tensors, but also there are techniques in tensor networks that basically helps you to break a very big multidimensional tensors. It helps you to break it locally and represent it in terms of a product of a smaller tensors, which have much fewer parameters. And for example, in depending on the dimension, it could be in 1 dimension, it could be It is called matrix product state in 2-dimension and 3-dimension. It is called PEPs, or projected entangled states, or in certain kind of basically tensor network, we could have hierarchical tree structures, or sometimes they are called MERA, or multi-scale entangled renormalization ansatz. But the thing is that if you look at this guy, this big tensor, it has n indices, and let's assume the size of each index is p, then the number of parameters in this tensor scales p to the power n, which is exponentially growing with the number of basically indices, which is suboptimal. It is not efficient, and on a classical computer, you will run out of space after a while. However, tensor networks allows you to break it locally and represent it in terms of the same p. However, with a new dimension that in quantum physics it is called quantum entanglement, or the correlation between different pieces of these tensors. And then the number of parameters in this network of tensors is actually, it scales polynomially with the p, n, and d, which is the entanglement that controls the amount of basically quantum entanglement between different pieces of the tensors. Now, a quantum state, basically any desired quantum state, such as a configuration of spins or any superposition of spins, can be represented with matrix product states. So this is one of the famous representation for the quantum states in the terms of tensor network. If you have heard ever of DMRG, or density matrix renormalization group, this is actually the form of the wave function that is being optimized in the DMRG algorithm. And basically it represents a very efficient representation for a quantum state, for example, for a spin system or a qubit system, which every one of them could have up or down. Okay, so we can use this tensor network to design an optimization problems, which is called TEBD, or time evolution block estimation. For this kind of problem, actually, you can have a cost function. Here, I show again you the Ising problem, because in any way we are interested to map our financial optimization cost function to these kind of Ising problems. And then you can actually use these techniques from tensor networks to basically find the ground state of this Hamiltonian or this cost function, such that the energy actually is being minimized. And then when you found the minimum energy, the solution, you can read it from these MPS, and then you will have a strings of zeros and one, which represent your optimal solution. So in this next slide, I have shown some references here that can help you to basically learn the details of this tensor algorithm. So the basic idea is that when we want to find the solution, we start from a random configuration of basically spins, or a random MPS or matrix product state, and then we apply some basically this exponential of Hamiltonian to this random state, and then basically we do it in a iterative way with setting this I to a real parameter tau. That's why this evolution is called imaginary time evolution. We break this operation to n pieces and apply it n times to this initial state, and then we end up into the psi tau, which is the final solution, and when you take tau to the infinity. So from the physics point of view, it's like you have a high temperature system, and then you cool it down, and then take it to the ground state of the system at 0 temperature, when tau goes to infinity, which is the inverse of temperature in quantum physics or in statistical physics. So this way, you can actually do the minimization for this cost function that you have. And the cost function is nothing but this h, which is, for example, your Ising Hamiltonian. So to show you how this is actually why it is called quantum inspired, and why it is very similar to what you can apply to quantum in quantum computing. Actually, this basically exponential operator, you break it to n smaller pieces, with tau basically goes to delta tau, which are very small, and then these are basically two-body gates, similar to the unitary gates that you have in quantum computing. And what you do is that you apply these unitary gates to the initial state. It's like a quantum circuit, actually. So you have some initial state, some zeros and ones, and then you have a certain well-behaved, controlled the unitary gates that you apply iteratively many times. This amounts to the imaginary time evolution that you apply these unitary gates to this initial state, and then you end up to your final solution. That this final solution is actually the ground state of your Hamiltonian, which is the cost function to your optimization problem. And then in the end, when you reach the minimum energy, you actually read the final solution. Basically, it could be a string of zeros and one that tells you that this is the solution to your problem. So this is the basic logic for the tensor network optimizer that we actually built and we solved to use optimization problem for the portfolios, for example. The good thing is that since these tensor network representation actually controls the amount of entanglement, it only captures the most necessary ones, discards the redundant entanglement, which are very small and not unnecessary. That's why it is very scalable, and you can actually simulate still this kind of many qubit or many spin problem on a classical computer. This is why, if you remember, I showed you in previous slide, not only the basically not only the D-Wave can solve this kind of problem, but also our tensor network solution on a classical computer can solve this. All right. So let me wrap up. So now that you have heard about all of these things, let me also show you our product. So Singularity, basically Singularity is the thing that I mentioned. We, knowing all of these and the needs of our clients, we created these kind of optimizers, and also on top of that, which I forgot to also mention, these the problem that I talked about here are a category of problem based on optimization. But of course, there are other categories of financial problems that can be represented, for example, with stochastic gradient, with stochastic partial differential equations, such as the problems that can be described by the Black-Scholes partial differential equation. Those kind of problems, people rather solve them by Monte Carlo or by machine learning. So we have also solutions that have been developed to use tensor network and quantum computing to target those kind of problems as well. So we created a tool which is called Singularity, which is our flagship product. It basically is a package containing a lot of optimization tools and machine learning tools that can be applied to different optimization or machine learning problems in finance, energy, cybersecurity, manufacturing, and many different places. So working with it is very easy. If you are interested to use so basically the user doesn't need to know anything about quantum computing. The user just need to select which quantum computer and which algorithm he wants to use. So basically it is hardware agnostic. Basically, typically the most flexible and largest scale one is the D-Wave. But of course, if you like, you can also use other computers such as IBM, IonQ, Rigetti, or Pascal, which is an atomic quantum computer, and then rather design your optimization problem with some simple line of code in Python, or just use the Excel sheet similar to what I showed you previously. However, this is not the only thing. So getting back to the machine learning part, so we learned that actually tensor network machine learning models are also very large scale, complicated, and very difficult for a classical computer. That's why we also use this tensor network to first reduce or compress the size of this machine learning model, as well as to use them for different purposes. Specifically for the case of, so you know, not only quantum these days are very important, but also generative AI and artificial intelligence, such as ChatGPT or different models that every day a new one of them pops out in the market. We also created tools based on quantum-inspired ideas that we learned from quantum computing for compressing these artificial intelligent models. So because they are very large scale, training them is very costly, working with them is also very costly. Also, I think there are limited GPUs in the world so that you could work with them. So we needed to make them more affordable and efficient, such that not only we use them for like daily use, but also we could deploy them for learning the behavior of the market, and then we could basically work with them to also address a financial problem as well. So we created Compactify, which is a machine learning or large language model compressor that basically it can help us to reduce the size of these models by 90%, increase the speed by to 8%, 8 times, and reduce the energy consumption. And all of this helps us to also target another category of problem with AI, not only quantum, but with AI armed with quantum-inspired solution. So that's why we created Compactify. So for example, if you are familiar with the large language model, like Llama, which is one of the AI models that is produced by Facebook or Meta, and we compressed it by 93%, reduced the number of parameters by 70% using our tensor network tools, quantum-inspired tensor network tools, and we were able to make it more efficient. And then one of the aims that we have is to use it to teach it to learn the market behavior so that it could predict basically the market behavior and used for solving basic financial problems. Okay, so this is me. I think we are up to our time, and then thank you for your attention.
Okay, thank you very much, Dr. Saeed, for your very amazing presentation. I think today's talks is give us valuable insights on how to use the quantum computing for the finance, especially Dr. Saeed introduced Tensor Networks application for finance that outperform for any classical computer, and also some hybrid quantum algorithm like FISIKA or KOLOKIUM. So thank you so much, Dr. Saeed. And we now have 30 minutes for our question and answer sessions. So to all the participants, if you have any questions, you can either post your question in the Zoom chat or raise your hand if you would like to ask your question directly to the speakers. Okay, so I see we have question in the Zoom chat. Let me read it out. The first question is from Kaisnan Ledito. So the question is regarding the tensor network approach. So as the TN approach adds another parameter D, how does D affect the data type or problem setup can be efficiently solved using TN approach?
Okay, so this is a very good question. So in principle, basically, if you are familiar with quantum physics, this D sets a limit to the basically size of the tensor. So tensor network usually works in the low entanglement regime. So like, for example, if the entanglement in your system is very large, it means that you need more parameter to describe this entanglement. So this D is also increasing. It means that the size of the tensors are increasing. So you need on a computer more computational resources to also run the tensor network algorithm. Okay, so this means that if you are dealing with a problem in a very highly entangled regime, tensor network would also face some challenges. But for many of the optimization problems that we deal with nowadays, I think they can be described by Kubo formalism, which are basically some sort of classical problem. Entanglement is basically very low. That's why tensor network in this kind of optimization problem performs very well. However, if you are simulating a material, or because I didn't mention here, tensor network can also be originally designed it to simulate quantum many-body system in the context of condensed matter physics. There are cases that the entanglement is very large, and then it is very difficult. Even for tensor network, sometimes there are challenging problems that tensor network might not always be the best solution. However, if you are dealing in a low entanglement regime problem, tensor network is guaranteed to produce very good and efficient solution.
Okay, thank you for the answer, Dr. Saeed. Is there any comment from Kaisnan Ledito? This okay? So if
thanks.
Okay, can I
thanks.
follow
I
up
think
the
it's good.
question? Okay, so if we're dealing with a larger entanglement, so it's possible how to solve the problem by using, for example, incorporating quantum machine learning or something like that one.
Yeah, so what we typically do is that on a classical computer, we let the entanglement to grow as much as our computational resources actually allow. So this means that, so we also have something which is called entanglement scaling. It means that we want to, for example, measure some quantity. we start running it for different size of D, and then we obtain different results, and then we do a scaling with the inverse of like a 1 over D or entanglement scaling, and it gives you a typical behavior, what would be the infinite entanglement behavior. So usually this is one of the typical ways that can give you an insight if you have a problem which entanglement is very large in it, but you cannot do it, like you cannot achieve infinite entanglement with your computational resources. You could still do some entanglement and give some overall insight, but usually for so like the machine learning problems and like many of the optimization problems for real world application, they are classical problems. Okay, it means that you can still target them with a small to moderate entanglement. There are cases, for example, studying dynamics of quantum states, that you want to study the time dynamic. Let's see how a state is evolving over time under the influence of some unitary gates or some Hamiltonian. This is a kind of problem that's as times goes, the entanglement can grow in your system, and then of course this means that tensor networks sometimes for a longer time or long time dynamics may face a problem. But using like maybe you cannot run it on your laptop, but you can still run it on a HPC, on a supercomputing center, and still get the very good result. But of course, as the times goes and the entanglement grows, things become a little bit more challenging and more computational resources needs. So that's why it's still, in the optimal case, a quantum computer can even outperform the tensor network as well. But until the best quantum computers are available, tensor networks are the most promising one from the classical worlds.
Okay, thank you, Dr. Saeed, for your explanations.
Yeah.
And we move to
You're welcome.
to the second questions from Dr. Agrum from Research Center for Quantum Physics. So the question is how the performance of the classical TN approach compared to the quantum algorithm in the financial problem you that consider.
So like, I think maybe there was a table explaining a little bit, so I can tell you the answer to this on the example problem that we had. Okay. So as you can see, for the very large scale problem, so this is the profit that it can tell you. So for example, so you know the quantum computer is actually capturing the real entanglement in your system on the D-Wave computer. So for example, for the largest number of assets for this dynamical portfolio optimization, there you would see that the quantum computers tells you that you might have it finds a solution that tells you you have 67% profit, but the tensor network solution tells you you would find a solution that gives you 39% profit, which the quantum solution here is better. But of course, I emphasize the results that you are seeing here is for our first implementation of the tensor network optimizer, which was not as good as today. I think with our current implementation, we obtained very close results from tensor network to the quantum. But of course, still the hybrid D-Wave quantum still is faster because it does the annealing using the ideas of quantum tunneling, and it finds the solution faster. But this is, for example, the paper that we studied at 2019. This is the difference that you can get from the, this is the tensor network, and this is the quantum computer, which was better. But of course, if you consider the Sharpe ratios, which is the profit divided by the volatility, you would see that they are not too different from each other, which is also, this is a signature that people usually use in financial industry for basically looking at the profit that they will gain for a certain volatility in the market.
Okay, thank you for the explanations. Can I follow up this question, Dr. Saeed?
Sure.
If I see the method that you consider, for example, the calculation for the Sharpe ratio in here, Gecko is classical, yes, right? So I mean that it's mean that if we just regardless the with hybrid and also tensor network, so it's mean that VKA or KOA is actually underperform.
Typically, yes, because first of all, because of the limitation in the number of qubits as well as the noise that you can have in those qubits. For example, VQ is that we used here. They are, I think that we used the IBM Quantum, and it was on their first generation of quantum computer. I think nowadays they are producing much better results because they have something that is called error mitigation. They basically equipped their quantum devices with error mitigation that suppresses the error from the hardware substantially. And I think there are a lot of results that shows that this error mitigation is essential. So I think the results that we produce here at that time, IBM didn't have error mitigation, and also the number of qubits was not as large as today. So these results are a little bit outdated. But if you repeat them on a quantum computer, even on IBM nowadays, I think the VQE has also been improved, also the constraint VQE. But yeah, so these results, you have to take it with a grain of salt because it is for 5 years ago.
Okay, thank you. And also, can you also give us the information about the how many asset, for example, XS and also until L.
Yeah.
Oh,
This table
okay.
tells you. Yeah. Okay.
Okay.
So for example, this is the number of assets. So for example, basically, this is the largest one had 53 assets over the the period of 8 years. So this is, I think, 2, 5, 7, 17, 29, and 53.
Okay. So it means that if you go to the previous slide, for example, if I use 7 assets, and then if we just using exhaustive
Medium.
classical, yes, this one, or for example as asset, okay, and then VKA is still underperform, right? So but for the case if you apply the constraints in here, so VKA constraint is outperform than exhaustive classical. So it's mean that I would like to ask what is the definition of the constraint in here and what is the parameter that you choose to improve the accuracy of the VKA?
So first of all, if you look at, like, for example, the profit, so for this M, which was the size of the 7 asset, you would see that if you use the VQE with constraint, you would get still 7% profit, which is a small. So it means that the optimizer finds a solution that tells you can at most have 7% profit. But if you go to better optimizer, for example, Tensor Network would tell you that there is a solution that gives you 15%. Of course, for example, if you look at this, because the size of the problem was not very large here, Tensor Network was better to search the parameter space. And if you can see here, the solution for Tensor Network is better than quantum computer. The one that I showed you here is for the largest one, which is highly difficult for the quantum computer as well as for the Tensor Network because it scales very large. But for example, for the M, you would see that Tensor Network even better than works better than for this medium-sized problem, better than basically quantum computer. For the constraint, I should remember correctly. But for example, if I get back to basically this cost function. So for example, the type of the constraint that you put here, so like this term here is actually introduces the constraint. So because it tells you that I want to find a solution for a basically fixed investment, total investment to be fixed, okay? And also you could play a little bit with these parameters that you see here, you put here, and also with the Lagrange multiplier or the transaction cost. If you fine tune these kind of parameters, you could still get rid of some of the variables and then make the problem size smaller. That's why you still have a constraint optimization problem, and the VQE constraint can handle it with fewer number of qubits. But without those constraints, it means that you needed more variable or more qubit, which was not available for the standard one. That's why it wasn't possible to do that. But the role of this constraint is to basically reduce the number of qubits and the basically variables that you need to define your optimization problem.
Okay, thank you. One question again, Dr. Saeed. regarding the constraints.
Mhm.
Can you elaborate more about the value that we need to determine risk aversions? Gamma,
Could you?
in your dynamics portfolio Hamiltonian, there is gamma, right? So it's mean like
So the gamma
yes.
here. Okay. So
Is there
I think if you
range?
read,
Is there range the
I
value?
think yes,
Yeah.
if I remember correctly. So if I remember, so this is something that actually we used some data from real market that our friends at BBVA from the bank they gave us. So it wasn't something that we just put it and play with it. This is something from real actual market values that we got from the bank, and then we use it to set the parameters of gamma here. So like, for example, the transaction cost, the gamma, these are the things that actually we used. So basically it is also telling here these data sets of different sizes. These data sets, we got it from the bank.
Okay. Oh, thank you. And there is
Sure.
question from the chat.
Okay.
Sorry for the question related to the business model. How does multiverse computing make a collaboration or cooperation with quantum computing hardware companies? Do you only focus on annealing type quantum computing companies such as the WIF, or do you also cooperate with the other quantum hardware companies providing different platform?
So basically, so as I mentioned, our solution is hardware agnostic. We have solution that can work basically on any quantum computer. Let me go to the last slide about singularity. I think singularity, if you look at this, so we have solution that can run on any one of them. So IBM or the gate-based superconducting computers like IonQ and Pascal are atomic quantum computer. D-Wave is a quantum annealer. Xanadu is a photonic quantum computer. So depending on the algorithm, basically we have developed something that can work in any of them. Okay, especially for the type of the optimization problem, you can run on any of them, and it's up to you. So for example, the reason that I mentioned D-Wave is because D-Wave is the most advanced bond in the market. It has the more than 2,500 qubit that can help you to solve a larger scale optimization problem. The rest of them does not have that much number of qubits. Okay, the reason that D-Wave is more suitable for this kind of optimization problem is because of the company of D-Wave, which is more advanced than the rest of them. But our solution does not really is not really limited to D-Wave. We also work with the rest of them, like for example, Pascal, Xanadu. They are our very close and good partners, and we develop different algorithms for different problems. Also, it is not only the optimization problem for finance that we use. We also use these quantum computers to, for example, on different problems such as simulating materials in quantum chemistries. For example, I think many of you are probably familiar with graphene, which is a very one sheet of carbon, and it has a lot of interesting properties that can be used in different sectors in industry. So, for example, we had a collaboration with IBM and also with the Pascal to simulate different kind of materials. So, for example, we developed a VQE on IBM to simulate graphene. And this is also the type of other problems that basically we work with them. And then so this is singularity. We have another tools called singularity material, which I didn't actually show here. That one actually is targeted for the quantum algorithm that are used, for example, for material. Like, for example, the type of VQE that you can define for optimization problem for financial industry is a little bit different than the type of VQE that you want to have for material simulation. The cost function or the Hamiltonian is different, and the parameters are different. That's why we have solution for all of them, depending on the and the good point, we build all of these tools according to the needs of our clients. Like, for example, we have clients in the market, we talk to them, and we create a solution for them, and then when they are happy and satisfied, we create a product out of it, add it to Singularity, and later we offer them like efficient solution to them. This is how basically we develop all of these tools.
Yeah, thank you. This Singularity is actually open source, right?
No, Singularity is not
no.
open source.
Okay. But the application is not only the finance, but also
No. The
okay.
application is basically in many different sectors. So we apply it to. So technically, what we do is that we talk with our client, we see what is their need, and then according to their need, we offer them the proper solution. So it could be material simulation, it could be optimization, not only in finance, it could be in logistics, it could be in many different approaches that basically one way or another, there is a type of optimization, for example, or machine learning. So these kind of things we offer with different variants to our clients.
Okay, thank you. And there is another question from Kaisman Ledito. Do you have any complexity comparison between TN approach and other type of quantum inspired algorithm, such as one from quantum is inspired linear algebra, if any?
Well, so the answer is probably yes, but not in the context of this problem. I think what we use. So I asked one of my colleagues to send it to me, but I think he was on holiday. I couldn't bring it to you. But for example, for a specific problem of optimizers, so we had for this portfolio optimization, we had an investigation to not only compare with quantum, but also compare our tensor network optimizer with different classical optimizer which are on in the market. I think for the moment, according to the advertisement and what is available in the market, there is this company. It is called Gurobi, which builds the best, or they claim that they have the best classical optimizer that you can find in the market, and also the GICO and also some other ones. Sorry, the classical optimizer in the market. So far, our tensor network is the fastest one among the companies that we are aware of in the market. But so I don't have the data to show you here, but we have such a thing. So I asked my colleague, but he was not available. Otherwise, I would show it here.
Okay, thank you. Is there any comment from Kaisman? Okay, enough. Okay, is there any question from the audience? Okay, maybe I ask a bit again, Dr. Saeed. Maybe a little bit outside the topic. I mean that if we try to consider external factor like, for example, geopolitical attention, and then like, for example, power speech and feed cut rate, and it will influence our strategy to investment, and how is robust the quantum classical approach for these cases if we try to consider external factors such as macroeconomic, geopolitical tension, and also some power speech, and also the feed cut rate.
Yeah, so this is a very interesting but yet difficult question. So as I said, so to address all of these things, you still need a mathematical model to consider all of these different factors for your financial model. Okay, so basically we call them model because we don't know what is the exact behavior. So if you can build a model that describes the market with respect to different basically factors that are out there in real world, one way or another, rather with this optimization or with these machine learning techniques, you can definitely find the actual solution, or at least an approximation to the solution. So for example, the thing that I showed you here is only a very a small part of the basically modeling for portfolio optimization. So you have, for example, you have American market, you have European market, and Asian market. So they all behave in a different way. They have Bermudan options. I don't know. So like vanilla options. Those are the kind of so basically economical models that applies to, for example, US market or to the European market, and hedging agencies and funding agencies, they follow those kind of strategies, and they have a model, they have a Black-Scholes partial stochastic differential equation. So these kind of models exist, but depending on the problem that you have at hand, there are different solutions. If it can be designed with the PDE or the differential equation, definitely machine learning techniques that can help you to solve those kind of partial differential equation are more suited. But if it is possible to map the problem to some sort of optimization problem, like such as Kubo, this kind of approaches are suitable. Not to also mention that Kubo means that you have binary problems, but we also have another category of problems that they are higher order of the constraint optimization problem. It means that every asset or every parameter or variable that you have in your problem can talk to each other. It's not only binary, but rather end-to-end. So it's like a graph problem. These kind of problems can also be used for describing more complex mathematical structure of the financial market, and as well as other things. We also have a different basically optimized tensor network optimizer that can also target those kind of problems, not only in the finance, but also for material simulation and things like that. So it's all about first defining a mathematical model, something that you can rather solve with some PDE, with some Monte Carlo or sampling. But if it falls into any of these categories, then definitely there is some sort of quantum or quantum-inspired solution that you can basically use with it. For example, I didn't mention the approaches based on Monte Carlo here because for the sake of time, it wasn't fitting here. But so there are also those kind of approaches that quantum phase estimation can come into place, and then instead of doing Monte Carlo, which is very expensive, you could do quantum phase estimation with a quantum computer, which could be even more efficient.
Yeah, thank you very much. Is there any question from audience, from the participants? We still have 4 minutes left. Maybe if there is no questions, maybe a little bit ask about the terminology about what is actually different between quantum optimization and also quantum inspired optimizations.
Okay, so I think this is also an interesting question. So quantum optimization is the optimization that you design and run really on a quantum hardware, like really on a quantum device and quantum computer. Rather, it could be a quantum annealer, or it could be a gate-based quantum computer, such as the superconducting qubit like IBM, or on a atomic quantum simulator, such as IonQ or Pascal or things like that. This is called usually quantum optimization. Quantum inspired typically means tensor network. Whenever, so these days, at least in the market, when you hear quantum inspired, it means tensor network. It means that tensor network, actually the base is coming from knowledge from quantum physics, because these are the ideas that it was developed in the scientific community, typically in physics community for simulating materials and quantum many-body system. But later people noticed that actually you can apply them also to optimization problem and those kind of problems that you can also run on a quantum computer. But for running quantum inspired, you don't need a quantum computer. You still use your laptop, your classical computer, you're using supercomputer centers. So quantum inspired, the idea is coming from quantum, but it is running on a classical computer. Quantum inspired is still classical. Okay, but quantum algorithms are purely quantum. They're running on quantum computers. So this is typically the difference. Also, quantum inspired or tensor network, it is not developed only in physics. I think there is a category in applied mathematics. Usually they call it tensor train or higher order tensor algebra. These are the things that in applied mathematics, they independently developed it, but they have different terminologies. They don't call it tensor network. They call it tensor train. So for example, in this case, like MPS that I showed you here.
Okay, thank you so much, Dr. Saeed.
You're welcome.
So I think we have 1 minute left, but I think it's okay. I think if there is any question from audience, I call again. Is there any question from the audience or participants? So icon. So if there is no questions, we will finish for this colloquium today. So thank you so much, Dr. Saeed, for your presentation, for your amazing presentation. So it
You're
gives
welcome.
us some knowledge about how to use quantum computation for finance applications. And we really appreciate your participation
Thank
as our speaker today to change the schedule of Prof. Roman actually. So I think
you.
with very limited preparation, but your presentation is very, very amazing today. So
Thank
thank you
you.
so
Thank you.
much for all the participants for joining us today. And we greatly appreciate your participations. And we look forward to seeing you again at our next BRIN Quantum Physics Colloquium. So thank you so much and have a great day, everyone.
You're welcome. And also thank you a lot for giving me this opportunity, and nice to see you all.
Okay. Thank you so much.